the previous class, we discussed and I derived everything, and we discussed the cyclotron motion. So, which is effectively if you have a charged particle and if it flies parallel to the magnetic field lines, nothing will happen, right? In that case, magnetic force will be zero. But if you have magnetic field like this, and particle flies perpendicular to the magnetic field lines, then the magnetic force will be perpendicular to the direction of motion, and the particle will experience circular motion, which we call cyclotron motion. It sounds cool, right, actually. Right. So, and we looked at one example, right? Then what's left undiscussed is a couple of conceptual questions. Right. Okay. Where are my markers? Here. So first, conceptual question 6, and then we will start discussing not Lenz's rule, Faraday's law. Conceptual question 6. It's still chapter 29. So what do we have here? Okay, let's start with part A. We have magnetic field into the board. Into the board, it's a bunch of crosses. Cross, cross, cross. So that's B. And of course, we want to discuss cyclotron motion, that right fancy. And of course, so particle must move perpendicular to this magnetic field, right? So it needs to enter perpendicular, right? So let's assume it enters over here. So we have a positively charged particle enters with this velocity v. I can put q, for example, but it's positively charged. You see plus in the circle. So the question is very simple, conceptual. Obviously, since particle moves perpendicular to the magnetic field, there must be circular motion. But circular motion that way or this way? We need to answer basically that question. Is it going to be bent upward or downward? So in order to answer that question, of course, we need to look at okay, I want to say Lorentz force, but magnetic force, expression for the magnetic force. Q V cross B, right? Basically, we just need to find direction of the force because this force is responsible for cyclotron motion, for this circular motion. If this force were not here, this particle would just travel along a straight line, according to the Newton's first law. But since force acts on that, of course, the particle will experience circular motion. And in order to find direction of the force, you remember we have to make 1.5 steps. First step, you need to look at the cross product, V cross B, find the direction of the cross product. And then once you know the direction, you need to look quickly at the sign of the charge. If charge is positive, then this direction is the direction of the force. But if charge is negative, then you need to flip this direction to the opposite one to get the correct direction of the force. So careful, don't forget, because still, even in the final exam, some students make that silly mistake when they forget to check the sign. Okay, in our case, charge is positive. So direction of QVB, direction of VB gives us direction of the force. Okay, direction of the V cross B. V that way, right? So I have to position my hand that way. Then I need to orient it in such a way so that I can bend my fingers into the board. So I have to position my hand like this, right? So now I can bend my fingers that direction. And my thumb gives me direction of the cross product. Right. So this is direction of V cross B. And again, since charge is positive, so this is positive. Let me emphasize, so it's positive. So it means that this direction is also a direction for the magnetic force. So this will be also F. Right. Okay, so if force acts that way, obviously, so we're going to have circular motion going sort of upward. Right, so this will be cyclotron motion, let me emphasize. So it's a cyclotron You know what? I want to use that for part B. Let me write it on this side over here. So it's a cyclotron motion. Right. Okay. So circle. So it's a part A for a positively charged particle. Now part B. B, magnetic field is now out of the board. Out, dots, bunch of dots. All right, dots, dot, dot. Okay, enough. It's annoying to draw so many dots. Okay, that's our magnetic field. So now it is out of the screen, out of the board. And of course, now we need to shove the particle. Let's assume now we have a negatively charged particle, electron, for example, right? So minus. And it travels this way with velocity v. The same question. First of all, obviously, it is going to experience circular motion because it moves perpendicular to the magnetic field lines. So cyclotron motion. The question is it going to move this way or that way? Again, that is determined by the direction of the force. Right. So again, I will write underneath. So F equals QVN cross B. Lorentz force. 1.5 steps again. First, direction of V cross B. Right-hand rule number 1. V is up, right? So I have to position my hand like this, but actually I need to orient it like that because now I need to match this direction. Direction is out of the board. So I have to orient my hand like this, and only now I can bend my fingers out of the board. Right? You see, out of the board. And my thumb gives me direction of the cross product, V cross B. V cross B, that way. Right? So let me use green to show the direction of V cross B, and then look at the sign of the charge. It's negative. Negative. So it means that in order to find correct direction of the force, this direction must be flipped. So force is to the right. So this will be the direction of the force. So it means that particle is going to experience circular motion bent that way. So also this is cyclotron motion. And actually, it's not just some silly conceptual question to torture you guys, right, to torture students. No, that's what experimental physicists who work with elementary particles, that's what they do. For example, right, you know those cloud chambers which are used to detect particles, right? So they can see traces this way or that way. So they know the direction of their magnetic field. They see the direction of the trajectory, right? So first they look at the cross product V cross B, and they see direction of the force because they see the curvature, right? So they can tell, okay, this must be negatively charged object, only in that case possible that direction of V and B and direction of force are opposite. So it means that particle must be negative. In this case, if direction of V cross B and direction of the force are the same, okay, it means that that particle was positively charged or is positively charged. It's a quite powerful, useful tool which physicists used, experimental physicists, right? And quite often on the final exam, I give something like this among multiple choice questions, asking, for example, I can give a trajectory and give what direction in direction of the magnetic field, and students should be able to tell if that particle positively charged or negatively charged, right? You see direction of the velocity, you see direction of the B, find the cross product. If the cross product in the opposite direction to the direction of the curvature, which is direction of the force, okay, charge is negative. If they are in the same direction, charge is positive. Okay, so that's what I was planning to discuss in the previous class, but because of the technical issues, we sort of didn't have time to do that. So now let's move to chapter 30, Faraday's law, new stuff, which we started discussing in the previous lecture, which was actually yesterday. So now Faraday's law. Actually, the chapter is called electromagnetic induction, but the major part is Faraday's law. All right. Okay, so let me first tell you what does Faraday's law describe. All right. So if you have, and it's a basically phenomena which Faraday observed, and in order to describe that phenomena, a new fundamental law was introduced because that phenomena couldn't be explained by what people knew up to that point. Right? So if you have conducting loop exposed to the magnetic field, some external magnetic field, right? Of course, if there is a area and the magnetic field, there must be magnetic flux. Actually, I will write in a second a review of the magnetic flux. And if that flux changes in time, growing or dying, current will be induced in the loop mysteriously. Right. And if there is a current, of course, there must be EMF, there must be potential difference, because current is a consequence of the potential difference. Current cannot appear just out of nowhere. There must be potential difference, right? Right. So it means that there must be somehow EMF produced in the loop mysteriously, and then current flows. Right. So that's what Faraday found. And Faraday's law was introduced to basically model. You remember, we just modeled the nature. God created everything somehow, right? And we just are using our tools try to model it. Okay, so, but of course, in order to write down Faraday's law, we need to introduce magnetic flux. We introduced that in the lecture. Now we just need to review that. Right. Okay, let me put a new bullet and, all right, so magnetic flux. Idea behind the magnetic flux is exactly the same like the idea behind electric flux. You just need to replace the word electric field with the magnetic field. That's it. Right. Okay, so let's imagine that what if I have um, some area, some loop. Okay, I tilted it. And which, as I just told you, must be exposed to some magnetic field. Okay, let me draw a few magnetic field lines. Right, so let's say this is B, right? And you remember the area vector which we introduced, I don't, a couple of months ago, I forgot, right? So that area vector must be perpendicular to the surface all the time, right? And the magnitude of that vector equals to the area of that surface, right? And since this surface is open, it's up to you. You can point area vector that way or this way. There are no restrictions. You have a freedom to choose either that direction or this direction. I usually pick in the direction of the magnetic field. All right, so let's say this is my A area vector A, right? Okay, so and now we can write the formula which mathematicians introduced to describe magnetic flux, right? And again, what's the meaning, sort of in simple words, the meaning of the magnetic flux? It's the number of these electric field lines crossing that surface effectively, right? The same like with the electric flux. Now, just replacing electric field with the magnetic field. Okay, so now we can write the formula. For this simplest case, when we have flat surface and uniform magnetic field. So magnetic flux sub B, because we use that's the letter we use to denote the magnetic field. So it's a dot product between B and the area vector. So that's what we will be using most of the time. We're not going to have some curved surfaces, right? Everything will be reasonably simple, uniform fields, flat surfaces. And of course, you remember, if you want to write it explicitly, it will be just BA and cosine of angle between these two vectors. So of course, we're talking about this angle theta. You remember, the tails of both vectors must be positioned at the same point in order to find the correct angle. Whew. Okay, now next, we introduce new quantity. And of course, what about units, the SI units? And again, now I can give you a speech about discrimination of electric quantity, of some physical quantities. Magnetic flux. Now we are going to write the special units. So units of magnetic flux, Weber. Right. But when we introduced electric flux, there was nothing, right? No, a special unit was not introduced. And of course, explanation is very simple, very practical. Magnetic flux is used to describe production of electricity. Production of electricity is everywhere. Tons of people use that, right? So in order to make their life a little bit easier, instead of pronouncing every time Tesla times meter squared, it's annoying. It's annoying, right? It makes sense to make their life a little bit easier by introducing like special unit. But electric flux, it is used mainly by physicists, right? Hardcore engineers, right? So it's not worth making their life is not worth of efforts, right? All right. Okay, so that's the magnetic flux, and now after this we can write down Faraday's law. Okay, Faraday's law finally. One of the fundamental laws. It's one of the equations from the set of Maxwell's equations. It means that you can use this law, this expression formula at any point of the universe, at any moment of time by anyone. And it must work. So far, no one has found any situations where it fails to work. Okay, so now let me write it down. So EMF. So again, you must have a loop exposed to magnetic field. And if, of course, there will be flux, magnetic flux. If that flux changes in time, there will be EMF produced in the loop. And of course, as a result, as a consequence, current will flow in the loop, right? But the law written for the EMF, of course, right? EMF equals to minus negative rate of change of the magnetic flux. So magnetic flux, put it here. And of course, if that flux changes in time, EMF is produced. Somehow, mysteriously, EMF is produced in the loop. Okay, let me, of course, frame it because it's a fundamental law. And of course, if you write it explicitly, it will be like this. So d over dt, b, a, and cosine of angle between them. So now I can say, if you want to produce EMF, induced EMF and induced current, it can be done in three ways. You can change magnetic field. So that external magnetic field to which loop is exposed, if this magnetic field changes, then EMF can be produced and current can flow. One situation. Second, what if you, for example, somehow change the area of this? Of course, I will never be able to change this area, right? But maybe something flexible. Maybe you can just change the shape, right? Or change the temperature. As a result, it will change. The area will change. So if somehow you will manage to change area in the loop, current will start flowing in the loop. EMF will be induced in the loop. Second situation. In the last situation, you can change the angle. In this case, basically, you will spin the loop relative to the magnetic field lines. If you spin that, angle changes and EMF will be produced. And of course, spinning is used in the current production, right? You know. Right. Okay, so what's next? Minus. Again, whenever you see minus, at least for me, they make me feel nervous, right? Because it means that I need to pay attention. I need to explain what does this or that minus means, right? So this minus mean it gives us a direction of EMF. Right. And dealing with that minus to get the direction of EMF is not very convenient, right? And if something not very convenient, sooner or later somebody will come up with some rule, some mnemonic rule in order to avoid dealing with something which is not pleasant, right? Just natural, right? All right, and so Lenz came up with the Lenz rule to avoid dealing with that minus. Basically, as a result, after introducing Lenz rule, we will split application of Faraday's law into two steps. First, we can find just the absolute value of EMF, and 5 volts, 10 volts, right, without taking care of the direction. And then you apply Lenz rule in order to get the correct direction of EMF and the correct direction of the current. Okay, so let me write that down. Minus shows a direction or gives a direction of EMF. Right. Okay, so to deal with that Lenz, which we wrote, came up with Lenz rule. Again, to avoid dealing with that minus. So he came up with this nice rule. And so as a result, application of the Faraday's law can be divided into two steps. First, you can find, for example, absolute value of the EMF. You see, I put a sign of an absolute value of that rate of change with minus. And the second step, Lenz rule. So that's what we're going to do most of the time. In the first part, nothing fancy. We'll just, for each particular case, we will look at a few examples. All right, but Lenz rule, we need to present it nicely. Actually, we spent like 15 minutes in the previous lecture introducing Lenz rule, and now let me sort of present in an accelerated version. Initial situation, again, conducting loop, and which is exposed to the external magnetic field. So this is the direction of the magnetic field, right? So this is the tip of the vector, basically, right? And two situations. So there is a magnetic field, there is a loop, of course, there will be magnetic flux. And the thing is, the system, in this case, the loop, doesn't like changes in the magnetic flux. It wants to keep the magnetic flux as constant as possible. If the flux is constant, then the loop is not going to do anything. Current is not going to be produced. The loop will be basically sleeping, right? But once you start changing the magnetic flux through this loop, of course, then the loop will wake up and it will start doing something, start responding on your actions, right? In which way? So two situations. Of course, flux can grow through the loop and flux can die through the loop. Two situations. So first one, growing flux. So if flux produced by this field is growing, the loop is not going to like it. It will respond immediately. So it will behave like a rebel. It will try to suppress the growing flux, trying to keep it constant. If you're growing, it will tell me, stop it, right? I don't like it, right? And how it is going to suppress? It will start driving current through itself, sort of like self-execution, right? Driving the current through itself. Not a pleasant experience, but anyway. Okay. All right, so it will start driving an induced current in such a direction. Right now, we don't know the direction, but we will find it. But we know, since it wants to suppress the growing flux, induced magnetic field will be in the opposite direction to the direction of the external magnetic field. Induced magnetic field is produced by the induced current. This current flowing through the loop, of course, must produce the magnetic field, induced magnetic field. And that induced magnetic field must be in the opposite direction to the direction of the external magnetic field. And in this case, the growing flux will be somewhat suppressed. It doesn't mean that the flux will be suppressed completely. No way. And again, why is it suppressing? Because since directions are opposite, flux produced by this external field, let's say positive, then flux produced by this induced magnetic field will be negative. If you add two numbers, of course, the flux will be somewhat suppressed. All right. Okay, so now once you know the direction of the induced current, induced magnetic field, external magnetic field we don't need anymore, we can trash it. So, because we know this direction. And of course, we know that this magnetic field is produced by this current. Of course, these directions are linked. How are they linked? Through the right-hand rule number 2. So we just need to curl our fingers around the loop properly so that within the loop, this direction and directions of my fingers matches. These two directions match. Right, so you see magnetic field is down, so my fingers must be down. So you see I'm curling my fingers around the loop. There are two positions. I can position like this, but now obviously directions is wrong. My fingers are up, but magnetic field is down. It's wrong. So I have to position like this. All right, and then you see my thumb, outstretched thumb, gives me direction of the induced current. So 3 steps. Let me again quickly repeat it all. So first, external magnetic field produces flux. Flux is growing. System, the loop doesn't like it. It will start driving the current in such a way so that the induced magnetic field in the opposite direction, suppressing. So it behaves like a rebel, like Che Guevara, right? I told you. And so now, once you know direction of the induced magnetic field, right-hand rule number 2, curl your fingers and outstretched thumb gives you direction of the induced current. Let me write this situation down. Basically, I want to write the train of thoughts which I usually write analyzing situations like this. So, first flux was, flux B was growing. So you see that arrow sort of going up. It means growing in time. First situation. And if flux is going, again, you remember the system rebels. In which way? It drives the current in such a direction so that the induced magnetic field will be in the opposite direction to the external magnetic field. You see? Arrows in the opposite direction, up and down. So I can write underneath, it rebels. Because again, you remember, it doesn't like changes in the flux. So now, once you know direction of the induced magnetic field, you can apply right-hand rule to find direction of the induced current. I induced, you can find, and using right-hand rule number 2. It's the same right-hand rule which we use to find direction of the magnetic field lines by an infinitely long straight wire. It's still the same rule. You remember, we outstretch our thumb in the direction of the current and curl our fingers around the wire. It's the same rule. But now we know direction of the field. And from the direction of the field, we're trying to get direction of the current. We just apply the same rule, but in sort of reverse direction. Okay, so it's a first situation. And of course, in order to find out what happens to the flux, here are 3 parameters, B, A, theta. We're going to analyze them. What happens with B, what happens with A, what happens with the angle. And then you jump here and go through this analysis. Now the second situation, when flux is dying. Okay, so now let me write down the second situation, flux is going down. Right, so now let's discuss that. Where are my players? Here and there. Again, initial situation, conducting loop, right? External magnetic field, which creates all this mass, right? Again, external, it means produced by something outside of the system, right? Okay, so, and a flux produced by this magnetic field is now dying, going down. Again, dying in time, right? Okay, so again, the loop is not going to like it because you remember it wants to keep flux as constant as possible. That's its goal. So it means in this case, so it sees, okay, you're dying through me. So again, it will start driving current through itself, like electrocuting itself. All right, but in such a direction, so that induced magnetic field and external magnetic field will be in the same direction, because again, now system becomes supportive. Since flux is dying, so it tries to use its internal resources to support a dying thing, like Florence Nightingale, right? Supporting dying soldiers, right? Let me help you, you'll suffer longer, right? Something like this, right? Okay, so now both of these directions are the same. Now, once you know direction of the induced magnetic field external, you don't care about that anymore. We can trash it. Because now what's left, the last step, you need to find direction of the induced current. Because this field is produced by this induced current. Okay, right-hand rule number 2. Again, you just need to match this direction. So I have to curl my fingers like this. Again, if I curl like that, it's wrong. Directions are wrong. Within the loop. Because you remember, we're trying to suppress the flux. Flux is within the loop. What is outside of the loop, who cares, right? Okay, so this way. So now my fingers, directions of my fingers, and direction of the magnetic field the same, and my outstretched thumb, okay, let me turn myself, gives me the correct direction. So direction of the induced current. So that's this situation. Okay, so now let me complete this. All right, so B, in this case, if flux is dying, so B induced will be in the same direction as B external. All right, you see the difference here. Directions are opposite, now directions are the same. So now it is supportive. The system becomes supportive. Yes, and I use that character like Florence Nightingale, Crimean War, the 19th century, right? That's where she became famous. All right, and then the last step from the direction of the induced magnetic field. Once you know this direction, you can apply right-hand rule to find direction of the induced current. So right-hand rule number 2. So that's Lenz's rule. And again, if magnetic flux is constant, then nothing will happen. The current will not be there. The loop will be completely happy, sleeping peacefully, right? But once you start increasing flux or decreasing, of course, the loop will start responding, start reacting, and start producing current. Okay, example. And then problems. Most likely on Monday we will continue playing with this, right? And most likely I will postpone the homework till Wednesday. Yeah, mainly because of those technical issues which we had in the previous class. So what if we have a conducting loop? And where is my container? Here's a container, right? I can draw. Wait, no, it doesn't stay. Okay, good enough. So that's my conducting loop. Of course, it must be exposed to an external magnetic field. Okay, and usually since we set up the experiment, right? So we usually decide what's the direction of the external magnetic field. So in this case, it's given. Direction of the external magnetic field is cross it's into the board. So that will be my B external. So B external. Right. And let's assume that this magnetic field, the value of this magnetic field is growing. So let's say it's growing. So initial situation, that's what is given. And now, of course, we need to answer the question, are we going to see any induced current? And if yes, then what's the direction of the induced current? And of course, the induced EMF, right? First of all, we need to understand what happens with the magnetic flux. That's the first step. Again, if magnetic flux is constant, then nothing happens. If it's growing, then we have to apply this. If it's dying, we have to apply that. And in order to understand what happens with the magnetic flux, you know what, let me write it here. I will separate like this, right? And I will continue over here on this side of the board because now I need some space. So 3 parameters, B, A, and theta. B, A, and theta. Pretty much first step, I want to get to this point. Area. We don't change the area of the loop. It stays the same in this process, in this situation, right? So area is constant, so it is not going to give us anything. It is not going to change the magnetic flux. Then angle. Angle between B and A. B and A. Area vector, of course, it's up to you. You can point it either out of the board or into the board. I usually align in the direction of the external magnetic field to make it 0 all the time, right? Again, it's up to you, right? We don't have any restrictions, but I usually align it like this. So let's say this is my A. Okay, in this case, angle is 0. But anyway, it's constant in both cases, right? If you make it 180 degrees or 0 degrees, anyway, it's going to be constant. It is not going to change our magnetic flux. Okay, maybe I will write 0 and then constant. 0 and constant. And yeah, this is external magnetic field, probably I should emphasize. Of course, external magnetic field, it's growing, it's going up. So as a result, B, A cosine of angle, since B is growing, so magnetic flux is going to grow. So it means that magnetic flux is growing. Immediately, it leads us to this first train of thoughts, to this analysis. So now I just need to go through that carefully, right? So magnetic flux is growing, so it means that this system is going to rebel, behaves like Che Guevara, right? It means that B induced magnetic field will be, you know what? I should have also emphasized what happens over here with these magnetic fields within the loop. It's very important. What is outside of the loop, we don't care. All right. So let me maybe, okay, I will write over here. It's within the loop. Within the loop. All this B induced, parallel, anti-parallel to be external, or parallel to be external. Again, it's within the loop because the system is trying to suppress the flux. Flux is within the loop, right? Okay, so now I can write, so B induced will be in the opposite direction to B external, right? Okay, so it means that opposite direction, so it means that within the loop I can draw a bunch of dots representing the induced magnetic field, and I will use red color. So bunch of dots with circle, right? So that will be my B induced. Bunch of dots. And again, you see, I drew them only within the loop. Okay, and now the last step, once you know the direction of the induced magnetic field, which is produced by the induced current, right-hand rule number 2. Right, so where is my loop? There, right. And see, now my induced magnetic field is out of the board. So we have this situation, out of the board. So now, in order to match this direction, okay, probably I will position like this, right? So I need to position my fingers like this to match this direction, right? Okay, let me stand in front, right? So, okay, maybe I will do it like this. Because if I position like this, it's a wrong direction, so I have to position like that. And my thumb gives me the direction of the induced current. So which is, from your point of view, counterclockwise. Counterclockwise. So now I can come up to the final conclusion. Counterclockwise, and in order to do that, I just apply right-hand rule number 2. Right. So it means that my direction of our induced current will be like this. I induced. So that's what I usually do all the time in order to let me move to this side. Analyze situations like this. Okay, so now let's look at problem 14 to practice more. So tomorrow in the lecture we will look at more examples, and then on Monday we will continue looking at these examples because it's one of the fundamental laws and important. All right, so you have to be very comfortable with these lens rules, and of course finding the value of EMF. Okay, so now let me erase this part of the board. And problem 14, it's also in your homework, problem 14, but I will look only at part A and probably C. But in your homework, you're going to look at all of those parts. Where is that problem? Here. So it's chapter 30, problem 14. 30, 14. Right. Again, we have a circular conducting loop. Radius is given. Usually we use R capital to denote radius, but since here we will also have resistance, I will use R sub 0 to denote a radius of the loop, right? Okay, so let me write. So we have part A, we have a conducting loop. Conducting loop. Radius is, actually diameter is given by, but I immediately convert it into radius. 5 centimeters. And of course, you will need to convert it to meters. At some point, sooner or later, it's better to do it now. 5 times 10 to the power of minus 2 meters. So it's a radius. And then resistance of the loop is given because we will have to find the value of the current. We will need the resistance. Resistance equals to, what's the value? 0.2 ohms. It's a reasonable amount of resistance of just a piece of wire. All right. And we also know, of course, it will be exposed to the magnetic field, which is into the board. I will draw the picture. You know what? Let me draw the picture immediately. All right. Okay, good enough. All right, so this is the center. And exposed to the magnetic field. External magnetic field is given, and direction is crosses into the board. So let's say this is our B external. Right. And that we know the rate of change of this magnetic field. It's a 0.5 Tesla, and it's increasing, magnetic field increasing. So what is given? So the absolute value of dB external over dt equals to 0.5 units. Whatever you see, Tesla divided by seconds. It's a rate of change of the magnetic field. Tesla divided by seconds, and it's increasing. That's it, what is given. So we need to find information about the current, direction, and the value of the current. So we need to find I, right? Not just a direction like what we've done over here, but also the value of the current, right? Okay, so direct application of the Faraday's law, new fundamental law, right? So we will have to apply two steps. This, of course, you can find first you can find the direction and then magnitude, or first magnitude and then direction. Let's do first direction and then magnitude. So first, let me find direction of I, right? So Lenz's rule. So again, we need to see what happens with the magnetic flux produced by the external field, and then the value. So B, A, and the angle, right? Exactly the same like here. A is constant. Area, okay, let me pick immediately area. Actually, it's almost the same situation, damn it. So area I will pick in the same direction as the external magnetic field, right? So area is constant, angle is 0 and constant, but external magnetic field is growing, it's given, it's increasing. So as a result, we can summarize this saying that magnetic flux is growing. So again, immediately it leads us to the first case, which we describe over here. It means that B induced will be in the opposite direction to the direction of the B external. So the system rebels. It means I can draw bunch of dots. Probably next class, I will just skip this example, just immediately dive into the problem 14. Right? And that's our B induced. Let me write over here. And again, you see I drew these dots only within the loop, because that's what we need. And so the last step, let me continue over here, right-hand rule. Exactly the same situation. So induced magnetic field is towards you. So I have to position my fingers like this to match that direction. And my outstretched thumb gives me direction, which is, again, counterclockwise. All right, so I induced CCW and applying right-hand rule number 2. Okay, so that's the first part. Now magnitude, or the value of I, or magnitude of I. Okay, now I can erase this. Okay, let's finish this value, and the rest will be on Monday. The first step, like now we don't care about the minus, because now we found direction of the induced current. Actually, I didn't show the direction, right? So this will be direction of I induced. Okay, let me hold you for a second, at least to show what must be done. So EMF equals to absolute value of d phi over dt. Minus I will drop. Flux B A cosine theta. Let me write that explicitly over here. So it will be absolute value of d over dt, B A and cosine of angle between them. What's the value of the angle theta? You see, I oriented my A vector into the board, so the angle is 0. So it will be just, okay, underneath I will write, or maybe above, theta equals to 0 degrees, right? So cosine of 0 is 1. So I can write immediately, so it's absolute value d over dt of just BA. Now, what can you say about the area? It's constant in time. We don't change it. B changes with time, but since A is constant, so we can extract it from the sign of differentiation. You can do it, right, from the mathematical point of view. And also area can be only positive, so we can extract it even out of the sign of absolute value. Area cannot be negative. It's a it's an area, right? So let me write. So A is, since A is constant, I can extract it from the sign. It will be A times absolute value of dB over dt. And actually, of course, you understand we're talking about the external magnetic field. Probably I should have emphasized external, right? Okay, area. We know the radius, it's a pi r naught squared, pi r sub 0 squared, and dB over dt is given in the problem. Originally, there, 0.5 Tesla per second. That's it. Basically, the problem is solved. So, of course, this is, let me emphasize, so it's a 0.5 Tesla per second. So, area is given, or not, radius is given, and area can be calculated. And if you do it, you will end up with 3.93 times 10 to the power of minus 3 volts. I used more sig fix because actually it's not the final result. We found what? We found EMF, units of volts. How can we find current? Ohm's law. EMF in the whole loop is given. We just calculated. Resistance is known. Ohm's law, banal now, right? So now the final step, I induced will be EMF divided by the resistance. And now I will use 2 sig fix. So it's a 2 times 10 to the power of minus 2 amps, or 20 milliamps. That's how it should be done. Okay, part B will be very similar, but in part B you will have this situation, right? And then part C we will discuss on Monday, right? And of course tomorrow in the lecture we will spend pretty much the whole class discussing this and looking at applications. Okay, sorry for holding you, but I just wanted to get this done.